Hello students, today we are going to discuss our remaining portions in hydrodynamics. So let's begin. In this figure, we can see a paperclip and an insects are able to float on the water. Even we know that they are denser than water. This phenomena can be explained by a characteristics of liquid, which is termed as surface tension. So let's discuss more about it in detail. We know that surface tension is an effect where the surface of the liquid is strong, and this property is caused by the molecules in the liquid being attracted to each other, and they form a elastic membrane like outer surface which tends to minimize surface area. In this figure we can see that the molecules in the middle portions attracts molecules all around it, while the molecules on the surface experience attractions only from sides and downwards. So we can say that surface tension is the tension of the surface of a liquid caused by the attraction of the particles in the surface layer by the bulk of the liquid, which tends to minimize surface area. So mathematically we can express surface tension as capital T is equal to F by L, where F is the force per unit length and capital L is the length in which force acts, and capital T is the surface tension of the liquid, and unit of the surface tension is equal to Newton per meter. We know that the unit of the force is known as Newton and the unit of length is meter. So unit of surface tension can be written as Newton per meter. So another one is surface energy. Surface energy. Surface energy is defined as the work per unit area done by the force that creates the new surface. So it is the ratio of work done by area or energy per area. So unit of the surface energy is written as joule per meter squared. Now we have to connect the relationship between the surface tension and surface energy formula. Surface energy is equal to work per area or energy per area. So the unit of energy is joule per meter squared. The joule can be written as Newton into meter per meter squared, and we can eliminate the meter. So Newton per meter, and the Newton per meter can be written as force per length because the uh, unit of force is Newton and length is meter. So from this we can get that surface energy equal to surface tension. And here we look some of the examples of surface tension. The first one is walking on the water. We already said that some insects which are denser than water but they can walk on the water due to surface tension. Then the other one is floating a needle, and this is also reason for surface tension. Then another one is soap and detergent, and this will help the cleaning of cloth by lowering the surface tension of water, so we can easily remove the dirts into pores and salt areas. And the other one is application of surface tensions. We can see that by the addition of detergents or soap, we increase the cleansing ability of the solution, and this happens when the detergent is added to water molecules. The water attracts and this will reduce the surface tensions. And another one is antisepsis, and this will also help to decrease the value of surface tension. And the other one is lubricants, oils and paints, which also lower the value of surface tension so that they spread over a large area. So we can see more application of surface tension in your textbook. And these are the factors affecting the surface tension. The first one is temperature, then the other one is impurities, then third one contamination, and fourth one evaporation and conduction. So first we have to uh, discuss the variation of surface tension with temperature. From this we can see that the surface tension of the liquid decreases with increasing temperature, that is surface tension is inversely proportional to temperature. The increased temperature decrease the intermolecular force between the molecules, that's why the temperature increases, surface tension decreases, and this variation vanishes when temperature is approached to critical value and it becomes zero at boiling point. For small temperature difference, we can see that the variation between the surface tension and temperature becomes linear, and it can be expressed as Tt equal to T0 1 minus alpha T. What Tt and T0 are the surface tension at T degrees Celsius and 0 degrees Celsius, and alpha is defined as temperature coefficient of surface tension. So if we can write as, from the above expression, we can write as alpha equal to T0 T by T0 T. Then by mathematical steps we define as alpha equal to minus 1 by T0 dt by dt, and dt by dt equal to minus alpha T0. Then another one is, we are talking about variation of surface tension with impurities. The variation of surface tension with impurities. When impurities added to liquid surface tension may either be increased or decreased, and depending upon the nature of the impurities. So we know that there are two types of impurities. First one is highly soluble and feebly soluble or insoluble. So we have to move first one, highly soluble impurities. The presence of soluble impurities may increase or decrease the surface tension. If impurities is less soluble, then the surface tension of the liquid decreases. Example, adding camphor to water. If the impurities are more stable, then we can set that the surface tension of the liquid increases. Example, when the salt is dissolved in water. So in the case of insoluble impurities, we can see that insoluble impurities decrease the surface tension. Example, if there is a dirt, grease or oil in the surface of the water, the surface tension will decrease. So from variation of impurities with surface tension, we can see that in high soluble impurities, the presence of surface tension may be increased or decreased, depends upon the impurities. If the impurity is less soluble, then the surface tension of liquid decreases. If it is more soluble, then the surface tension of liquid increases. But in the case of insoluble impurities, we can see that it is always decreases with surface tension. And the third one is contamination. Contamination or chemical addition. Adding chemicals to a liquid will change its surface tension characteristics. The effect of adding an chemical to a substance, there will be changing its surface tension, and the value of the surface tension depends on the degree of contamination. Example, if we putting a soap or a surfactant in water to reduce surface tension, which allows the dirt on your hands to more easily mix with water. Now we have to derive the expression for excess pressure inside a spherical liquid drop and inside a soap bubble. And from this expression we can found that the excess pressure inside the liquid drop is 2 times than the surface tension of the liquid over the radius of the drop. But in the case of soap bubble, the excess pressure is 4 times the surface tension. So excess pressure inside a spherical liquid drop is 2 times the surface tension. In soap bubble it is 4 times the surface tension. So now we are going to derive the mathematical expression for the excess pressure acting in a spherical liquid drop and a soap bubble. This is an important derivation. You have to learn it thoroughly. In your textbook the derivation is not explained well, so please follow this theory section with importance. So first we have to derive the excess pressure inside a liquid drop. First we have to consider a liquid drop of radius capital R and S be the surface tension of the liquid drop. Here we take capital S be the surface tension. In your textbook we can see that T be the surface tension of the liquid drop. So there is a small change, and capital P is the excess pressure inside the drop, and due to this excess pressure we can see that there will be increase in radius of the drop by a small amount, and that can be expressed by delta R. So we have to write work done by the excess pressure. Work done by the excess pressure equal to W equal to force into displacement, and force can be written as pressure into area. So excess pressure into area into increase in radius. So excess pressure is capital P into 4 pi r squared, and increase in radius is delta R. And increase in surface area of the drop is change in final surface area minus initial surface area. So final surface area is written as 4 pi capital R plus delta R whole squared minus 4 pi R squared. The R plus delta R whole squared can be written as A plus B whole squared, that is A squared plus 2B plus B squared. By calculating we get 8 pi capital R delta R by neglecting delta R squared being very small, and then we written as increase in surface energy. Increase in surface energy, we know that surface area into surface tension. Increase in surface area, we already found that 8 pi capital R delta R into surface tension is capital S. So by equilibrium we equating 1 equal to equation 2, that is P into 4 pi R squared into delta R equal to 8 pi capital R delta R into S. And by substituting and by mathematical steps we written as capital P equal to 2 capital S by capital R. In your textbook we can see that capital P equal to 2T by R. So we found that inside a liquid drop we can see that excess pressure is towards the surface tension. And there is a special case inside a bubble in a liquid. Consider a air bubble of radius capital R just inside the liquid of surface tension X. Here also the excess pressure is inside the air bubble can be expressed as capital P equal to 2 capital S by R. And another one, we have to derive the expression of the excess pressure inside a soap bubble. So same as the liquid drop, we consider a soap bubble of radius capital R and S be the surface tension of the soap solution, and capital B the excess pressure, and due to this excess pressure there will be increase in radius of the bubble by a small amount of delta R. And due to excess pressure we can see there will be increase in radius of the bubble, and that can be represented by delta R as same in liquid drop. So work done, here also we written as work is equal to force into displacement, and force is written as excess pressure into area, that is P into 4 pi R squared into delta R, and there is a increase in surface area, that is final surface area minus initial surface area. But only difference is 2 into final surface area, because the soap bubble has two free surface, one outside and one inside. So the effective increase in surface area is double the final surface area minus initial surface area. The only difference in liquid drop and soap bubble is 2 times in soap bubble, because they has two free surface, that is 2 into 4 pi capital R plus delta R squared. By neglecting delta R whole squared we written as 8 pi into 2R delta R, that can be written as 16 pi capital R delta R, and we written as increase in surface area, that is increase in surface area into surface tension, that is 16 pi capital R delta R into S. and by equilibrium we writing as equation 3 equal to equation 4. That is P into 4 pi capital R squared into delta R equal to 16 pi capital R into delta R inverse by cutting 4 pi 16 pi R delta R we written as P equal to 4S by R, that is excess pressure inside a soap bubble is 4 times the surface tension over the radius of the bubble. And thank you students for listening this, and if you have any doubt don't hesitate to ask me. Thank you.